Okay, so we will be recording this session, and now we're going to be talking about another method for circuit analysis, which is the superposition theorem or superposition analysis method or superposition analysis. And the superposition analysis is based on a theorem, okay, that's called the superposition theorem, okay? And basically the superposition theorem, before we talk about the superposition theorem in circuit analysis, the superposition theorem, if you're gonna remember it and remember it for the exam, the superposition theorem is basically equivalent to divide and conquer, okay? And what does this mean? The superposition theorem in systems engineering, in systems theory, says that if I have a system, the system has to be linear, by the way. The system has to be linear. And linear, when we talk about a linear system, remember that linear systems have a mathematical definition. They are these systems that can be represented mathematically in a certain way and have certain properties. One of their properties is the superposition theorem. And so the superposition theorem says that if I have a system that has many inputs or stimuli, the total effect or result of each of those individual stimuli, combined stimuli, is equal to the sum of the individual effects, okay? Or the individual contributions. This only happens for a linear system. Okay, this only happens for a linear system. And so what's happening here is that if I have a system that has three inputs and the system is linear, the resulting effect of these three inputs is the same as analyzing and adding the effects of each of the inputs separately. Okay, and so that's why it's the divide and conquer. We can have the analysis of a system if it's linear, and I can analyze the system in parts and then just add up all of the parts, and the resulting effect is going to be equal to the sum of the parts. So in circuit analysis, the superposition theorem states that a circuit with multiple voltage and current sources, so I have multiple sources of energy or power within the circuit, is equal to the sum of the simplified circuits using just one of the sources at a time, okay? Meaning that if I have a circuit that has two voltage sources, and I want to see the different currents and voltages that are interacting in the circuit, I can first analyze the circuit with one power source, take note of the components and the results and the effects. And then I can analyze the circuit with the other power source, take notes of the effects and the variables, and then just add them up. And that's going to be the resulting effect. Okay, so this can be used for circuit analysis. Now, some guidelines to follow, and I'm going to do an example here, is that first we're going to do a separate analysis for each power supply, where we eliminate all of the other power supplies. So we're going to do a separate analysis of the circuit for each power supply. For each analysis, we're just going to leave one power supply and eliminate the rest. How do we eliminate them in circuit analysis? The way we eliminate them is that the voltage sources are short-circuited. So basically, instead of the voltage source or power supply, we're just going to remove it and put a cable there or a line. Right now, for this study of superposition for this course, we're not going to be talking about current sources. We're just going to be focusing on voltage sources. Next semester in industrial electronics, we're going to be seeing more complex examples. But right now, we're going to be talking about voltage sources, and those are short-circuited. If it were a current source, we would open the circuit to eliminate. And lastly, we're going to add up all of the individual results for each analysis. Okay. Okay. And so that's going to be in general what we're going to be doing. Now, by the way, disclaimer, I need to mention this, and this is going to be recorded. This is a topic within the course, superposition theorem. In my humble opinion, this topic is really not necessary in this course because, again, you are going to be taking an industrial electronics course next semester where you go deep into circuit analysis, okay? The other reason is that since this is just one topic in a course that has too many topics, there's really not enough time to go deep into it. And we're going to see an example here. And you're going to notice that solving this example using the superposition theorem is going to be longer than the other two methods that we already saw, which is mesh and node. It's going to be the same example. We're going to take much longer to solve it using superposition. It's actually, in my opinion, going to be more complicated. However, the real application of superposition theorem, of the superposition theorem, is this principle that if I've got a lot of elements in the circuit, it does help me out to eliminate these and analyze them separately if I want. But said in more simpler terms, the superposition theorem is going to be it's going to be more bother than it's worth, but we're going to see it. Ankel's mentioning that we should skip it. We're not going to skip it, but we're going to put it into context and just for you to understand how it's used. Okay, so we're going to do the same example we've been working on in the previous two methods. So we saw the circuit, this circuit with mesh analysis and node analysis, and we went through the solving of the circuit, and we got exactly the same results. We're going to do exactly the same thing, but now using superposition. Now, the important thing here to start off is that this circuit has, we need to identify the power supplies. We've got two power supplies, the 10-volt power supply and the 20-volt power supply. That means that we're going to do two analyses. One with the 10-volt power supply, where we're going to eliminate the 20-volt power supply, and one with the 20-volt power supply, where we're going to eliminate the 10-volt power supply. Once we're done, we're just going to add up the results, and that's going to be the final result. Okay, so let's start off with the first analysis. So for the first analysis, we're going to eliminate. Oh, before we do that, what are we trying to find? We're trying to solve the circuit. So again, we're trying to find, for this example, we are trying to find the three currents. There's three currents here. These are what we have been trying to find in the previous, using the previous methods. We've got three currents, and we want to find those three currents. Okay, and so the first thing we're going to do, the first analysis, is we're going to eliminate the 10-volt power supply. We're going to eliminate the 10-volt power supply. How do I eliminate it? I'm sorry, we're going to do the analysis, with the 10-volt power supply. That's what means we're going to eliminate the 20-volt power supply, which was originally here. How are we going to eliminate a power supply for superposition analysis? We're just simply going to put a cable there. We're going to short circuit it. That's the way we're going to eliminate it. By the way, I didn't mention explicitly, but this circuit, to be able to use superposition, has to be a linear system or a linear circuit. How do we know it's a linear system? Because all of the components individually that we're using in the circuit are linear. Why are the power supplies linear? Because they're constant. Why are the resistors linear? Because the resistors are governed by Ohm's law. Okay, remember that Ohm's law governs the relationship between resistance and voltage and current, and this is linear. Okay, and so if all of the components that I have in the system are linear, in this case, the circuit is going to be linear. If this circuit had some capacitors and inductors in it, we'd be talking about something else. But for now, this is an example of a linear circuit. That's why we can apply superposition. So that's the first thing we do. We eliminate this. Now, since we're doing just part of the analysis, I'm going to tag, or we're going to tag or name these three currents, which originally were I1, I2, and I3. I'm going to add another index here to call them I11, I21, and I31. This second subindex that we're adding here means that we're talking about the values for analysis number 1. Okay? Okay. Once we do this, we have a new circuit that we need to analyze. Now, how can we solve this circuit? We can do it many ways. I'm going to do it just simply doing a reduction and simplification of the circuit using the laws that we have. The combinations of resistors in series and in parallel. We could also do it by mesh or node analysis, whatever analysis we want to use to find what we're looking for. But once we have this, then the next step is to start to analyze the circuit and find those three currents. So what I'm going to do is that, just to practice, I'm going to do the simplification of the circuit, okay? So first off, to do the simplification, we're going to try to find an equivalent resistance. And once we find an equivalent resistance and a total current, we're going to go back and find the individual currents. And so first off, question for you guys. This was in the exam. What type of connection is this? Can somebody tell me? Series or parallel?
Series.
No.
Parallel. That's what I got wrong.
Yeah, exactly. JC, you remembered, and actually remember that I explained this. I explained it to you via WhatsApp, and we talked about it here. A lot of you got this wrong in the exam. This is a parallel connection. Why is it not series? It's not in series because we've got a node here where current is we've got a node here and a node here where the current is being separated. Okay. Now, this would be much simpler for you guys to understand, I think, if this circuit were to be drawn this way. So it was purposely confusing, not purposely confusing, but it could be confusing. So if I drew the circuit this way, would it now be clear that, and let's say that this is the 40 ohm, and this is the 20 ohm, and this is the 10 ohm, and this is the 10 volts. Would it be clear now to everybody that these two are in parallel? Well, it's exactly the same thing. The only thing is that I'm moving this one up here, but it's exactly the same connection. The two terminals are connected to each other. So it's a parallel connection, the one we've got there. So that's the first thing I'm going to do. We're going to reduce this here is a parallel connection. So I'm going to do that reduction. We're going to grab this and we're going to reduce that or simplify that. So we've got a parallel connection there. So this is going to turn into this. And that resistor, since it's a parallel connection, we're going to have a parallel combination there, which is the equivalent resistance is going to be 1 divided by 20 plus 1 divided by 40, the reciprocal of that, because remember that we're talking about the sum of the reciprocal of the sum of the reciprocals when we're in parallel with resistors. Remember that this is the other way around than the capacitors. And so that gives us 13.33. Okay. Now, the next question, what is this combination here? How are these two connected? Series or parallel? Again, how are these two connected? How are these two resistors connected? In series or in parallel?
Like that alone, series, right?
In series. Just those two are in series because there's a current flow here that isn't interrupted. So the current is going like this, so there's no interruption. So it's a series connection. So now we're going to do the combination of those two. And that's going to give us one, the equivalent resistor, which is going to be this one, which is going to be the series combination of the 10 ohms and the 13.33 that we just found. And so the equivalent resistance is going to be equal to, this is the equivalent resistance, or the total resistance is going to be 23.33. Now, this is the equivalent circuit, and I know that there's a current flowing through this circuit, okay? So that's the steps to do that reduction. Now, I know that, let me just leave this here. I know that there's a current going through the resistor, okay, or the equivalent circuit. I know that there's a current going through here, and actually that's this same current I11 that I'm looking for. How do I find that current? Well, that current is going to be simply out of Ohm's law. It's going to be the voltage, which is the 10 volts divided by the equivalent resistance. So I11 is 0.4286 amps. So we just found that one. This is the total current going through the circuit. And now we're going to go backwards. With this current, now I'm going to, so let's say that first we were going clockwise, step one, step two. And now once we find the equivalent resistance and equivalent current, we're going to start to unravel the circuit and go back. So now we're going to go back. And since now we have this current, this is going to be the same current that's going to be flowing through here. It's going to be exactly the same I11 that's flowing through this part of the circuit. And we're going to have a voltage here in this element. We're going to have a voltage that I'm going to call Vx. Okay. I'm going to call Vx. And this voltage, by the way, that I'm calling Vx, since current I11 is going like this, is going to have the following polarity. It's going to have a positive and a negative polarity because the reference we've been taking is that the current is going into the positive. And how would I calculate the voltage in this element? Well, it's going to be through Ohm's law. So it's going to be through Ohm's law. And I know that that voltage is going to be equal to the 6.66, moment here, I need to, oh, let me correct something here. It's I11. Okay, let me correct something here. I had done a copy paste here of some calculations. Let me correct something here. Give me a moment. This is actually the 13.33, and this is the one that we just found, 0.4286. Okay, give me one moment here. All right. Sorry about that. I'd done a bad copy paste there, and there we go. Okay. So it's going to be the 13.33. 13.33 ohms that we had up there. The 13.33 ohms, which is this resistor, multiplied by the current that we just found, this is going to give us 5.7143, which is going to be the voltage in this element here. Okay.
¿Cómo se prende el switch?
¿Pero por qué hablas como persona?
Lee.
Tráeme el switch y te lo prendo, pero estoy en clase. Okay. So we've got this here, 13 point, this is going to be the voltage here in this element, okay? And the polarity of that voltage is going to be given by plus minus. Now, since we now have the voltage in this element, now we go back, also now we go over here. And so we separate now. And so this voltage Vx is going to be the same voltage that I have in these two elements. So because they're in parallel. So this element is going to have Vx. And this element is also going to have Vx.
Professor, I got a question.
Yes, go ahead, Carmina,
Where
please.
did you get the 16.66?
Could you say that a little bit louder? You're a bit far from the
Where
mic.
did you got the 16.66?
Where did I get the 16.66? Where is the 16.66? If you could mark it.
The
Oh, I'm
10
sorry.
divided by-
Yeah, that's also, yeah, good observation there. Again, it's part of the copy paste thing. Give me a moment here. Yeah, this is the 23. Thank you, Carmina. That was also yeah, I'm gonna correct that. Thank you, Carmina. That was also so here we're talking about these values here. So it's actually 10 volts divided by the 23.33, which is the resistance that we have. Thank you for that. Thank you for that observation, Carmina. Okay. Okay, so going back, we've got the plus and the minus here. This is going to be Vx. So now if we have the voltages, if we have the voltage that corresponds to these two elements, we can find the currents. And so current I21 is going to be the voltage, which is 5.7143 that we already found, divided by 20. But it is going to be negative. Can somebody tell me why it's going to be negative instead of being positive?
It's going from right to left.
Because it's going exactly, Carmina. And again, your microphone sounds a bit far off. But yes, we're going from left to right. So we're entering through the negative here, at least the way we established the current. So that's why it would be negative. And next we've got I31, which is going to be the 5.7143 with the 40 ohms. That's going in through the positive and out through the negative. So this gives us 0.1429. Okay. These three values, these three values that we just found here, we're going to keep them, or we're going to write them down somewhere, because this isn't the final result. This is just the result of the first analysis, okay, where we find the three values. This is the contributions to those three currents when we just have the 10 volt power supply. So those are those three. Okay, we're going to keep them, take note of them, and then we're going to do the analysis for the second one. Okay, before we jump to that, questions with this one? Okay, I'm going to clear this and jump to the next one. Okay, so analysis number 2, now we're going to eliminate the 10 volt power supply, which is the one that was here. How are we going to eliminate it? We are going to eliminate it by putting a cable there, just a connection there. And the same as the other one, we're going to have the three currents, I1, I2, and I3, but now I'm going to use another sub-index. I'm going to call them I12, I22, and I32. And why? Because these are going to be part of analysis number 2. Okay, which is going to be with the 20 volt power supply. Okay. So now we've got the circuit. We're actually going to do exactly the same procedure we did with the other one, but now with the 20 volt power supply and the circuit's arranged this way. So similar to the other circuit, we've got these two here. How are these two connected? Can somebody tell me?
Parallel.
Parallel, hindsight. Hindsight is always 20/20, perfect. And we have to remember that. Those are in parallel. We are going to grab those two and we're going to generate an equivalent circuit where this resistance is going to be this one here. And the calculation, since those are in parallel, it's going to be, it's going to be the reciprocal, the reciprocal of the sum of the reciprocals. Okay, that we've got here. And that's going to be this element here. Okay. And next up, these two, how are these two connected? How are those two connected?
In series.
Series. Okay. So these now are in series. They're going to be in series because again, the flow of the current isn't going to be interrupted. Okay. So now we take those two, we bring them over here, and we're going to have the equivalent circuit, which is going to be this one. We're going to have the equivalent circuit with one equivalent resistor. This resistor is going to be equal to 20 ohms plus the 8 ohms, which is going to give us these 28 ohms. And that gives us the equivalent resistance for the whole circuit, okay, which is this one here. Now having the this is going to be the equivalent resistance. Now, once we find the equivalent resistance, now we're going to find, or we're going to try to find the total current in the circuit. And so we know that there's going to be a current that's going to be flowing through this circuit, okay, that we're going to call I22, which is actually this same current that we've got here. So notice that it's this current, the current that we're looking at. And that current, how do we find it? Well, we can use directly Ohm's law with the 20 volt power supply and the equivalent resistance. And so we've got 20 volts divided by the 28 ohms. We've got 0.7143 amps, okay, which is the current for that element, okay. Now, again, similar to the other one, now we're going to start unraveling. From here, we're going to go back here, and we're going to see that this current is the same current that's flowing through these elements here, which is going to be I22. And we're going to identify that there's going to be a voltage in this resistor. That voltage is also going to have a polarity that's going to be plus minus, because the current is going through in through the plus and out through the minus. And we can find the value of that voltage. We can find the value of that voltage by using Ohm's law, which is going to be 8 ohms multiplied by the 0.7143, which is the current. And so we find that. Once we find that voltage, now we're going to go back over here to the original circuit, and that voltage is going to be the voltage that we have in these resistors. This is going to be Vx, which is plus minus. It's going to be also here. It's going to be the Vx here that we've got in this resistor, Vx. It's also going to be the same Vx that we have in this resistor. Again, because they're in parallel. Remember that the resistance, the voltage is the same in parallel. So coming back to that, we've got the voltages in those two resistors, and we can find the current. So we can find current I2 is going to be the voltages we just found Vx, 5.7143 divided by 10. And this is going to be negative. Why is it negative? Because it's going in through the negative and out through the positive. And we can also find I32, which is going to be the 5.7143 divided by 40. And that's going to be going in through the positive and out through the negative. It's going to be positive. We've got 0.1429. And so now we've got another 3 currents, which is going to be this one, which is going to be this one here, this one here, and this one here. And those 3 are the contributions that have to do with the 20-volt power supply. So we did the analysis with the 10-volt power supply, and we've got 3 currents. We did the analysis for the 20-volt power supply, and we've got 3 currents. We've got both contributions. And the superposition theorem says that because this is a linear system, we just need to add those algebraically. We need to add those, and we're going to find the total solution, or the total contributions or results. So we're going to do that. From analysis 1, we have these 3 currents that we found. From analysis 2, we've got these 3 currents that we found. Therefore, because of superposition, we just add them. I1 is going to be I11 plus I12. We add them, including the signs. It's an algebraic sum here, and we've got minus 0.143. We add I2 is going to be equal to I21 plus I22. We add these 2 that we found. We get 0.429. And I3 is going to be I31 plus I32. It's going to be these 2, which is actually the same, and we get 0.286. These 3 are exactly the same values that we found with the other 2 analysis when we did mesh and we did node analysis. Okay, so what we've done here is that we've taken the same circuit and we've done the analysis of the circuit to find the values with 3 different methods: mesh, node, and superposition. Now, again, if you notice, the superposition method was the longest one and maybe the most impractical one, but we still got to the same results. Everybody has their preferences with regards to the methods. I particularly am a mesh guy, so I prefer mesh analysis whenever I'm going to be doing the analysis of the circuits. Other people prefer other methods. In the end, you're going to get to the same thing. It's just different ways to approach the analysis.